So, good day, everyone. So, let us continue our discussion on emerging technologies, especially on geographic information system. Okay, so this is the outline of our topic for this week. No? We'll discuss the GIS data, types of GIS data, the examples of GIS data sources, remote sensing, applications of remote sensing, what is GPS and GIS integrations. We will define LiDAR and aerial photography, OpenStreetMap and crowdsourced data, methods of data acquisition, and factors that affects the data quality in GIS. So basically, GIS data again refers to the information that is spatially referenced, allowing it to be associated with specific geographic locations, including both the attributes and spatial coordinates no, of features on the Earth's surface. For example, the vector data and the raster data. Again, GIS data refers to the information that is spatially referenced. No, so that's the GIS data. So again, here are the two types of GIS data: the vector and the raster. When we say vector data, we have here the points, the lines, and the polygons. Point data, GPS coordinates of landmarks. Line data, these are the roads, rivers, and pipelines. The polygon data, it's the political boundaries and land parcels or land areas. No? On the other hand, raster data, these are the satellite imagery of the Earth and elevation models. Okay? So these are the common data sources of GIS. We have census data, satellite imagery, topographic maps, geospatial surveys, and publicly contributed data. Ano ba itong census data na to? So these are demographic informations that have been collected by various government agencies, for example, NAMRIA, MGB, DRRM, DLG, no, uh, and other agencies that require GIS data to perform their responsibilities. Okay, so that's census data. These are collected by government agencies. Second one is satellite imagery. Ano naman ito? So these are images that obtained from Earth observation satellites. So these are again mga satellites na nag-orbit around the Earth. No? Meron silang kinukuha mga imagery using their satellites. Third one is topographic maps. Itong topographic maps na to, these are detailed maps illustrating surface features. For example, a rolling mountainous area, idle area, forest area, yung ano tawag dito? Bathymetric map. No? So those are topographic maps. No? Detailed maps illustrating the surfaces features. Okay, kung mabundok, kung rolling, kung mountainous, and those are the sample of surface features. Fourth one is geospatial surveys. These are ground-based surveys using GPS technology. So these are field surveys, no, on the ground data collection or gathering. They use GPS technology or the global positioning system technology, through ground surveys. So these are geospatial surveys. And the last one is publicly contributed data. These are data from platforms like OpenStreetMap, Google Earth, Mapbox. No? So those are contributed data. You know? These data came or come from volunteers. No? So these are the five GIS data sources: census from the government, satellite imagery from satellites, topographic maps that illustrate surface features, geospatial surveys using GPS, and publicly contributed data coming from volunteers. So now let us discuss remote sensing. this satellite imagery and aerial photography. When we say remote sensing, no, it involves the collection of information about an object or phenomenon from a distance. No? Medyo malayo or malayo siya. Typically, through the use of satellites, aircraft, or other sensor technologies, it enables the capture, no? Of data without direct physical contact with the subject. No? Ang purpose naman na to ng remote sensing is to gather data on Earth's surface and atmosphere for analysis and monitoring. Okay? So example nga ng remote sensing natin is satellite imagery that captures detailed images of the surface of the Earth, and aerial photography that gathers high resolution, takes high resolution photograph taken from an aircraft. No? So again, remote sensing involves the collection of information about a phenomenon from a distance. No? Typically, they use satellites, aircraft, or other sensor technologies. It enables the capture of data without direct physical contact with the subject. So, to give you more idea what remote sensing is, let us watch these two videos. Okay?
Remote sensing is observing a medium, a process, some phenomenon without ever coming in direct contact with that phenomenon. So unlike a lab experiment or where you go to a place and make an in situ measurement or actually touching the medium, remote sensing is observing it remotely from a distance. And this actually provides a different kind of perspective on things. When you're part of your medium, you're part of your experiment, you're part of the experience, you get one perspective that's crucial. You get a very different one when you're removed from it, when you're looking from space, when you're looking from 400 or 500 miles away, or in some cases 20,000 miles away. We can start up close, we can stand in a place and look at it, and we can zoom out, and all of a sudden it takes on new meaning. The trees are part of a broader system that sit on a landmass that is a country, that's part of a continent, that sits in an ocean. And as we step back further and further and look at those same trees, we may not see the leaves from far away, but we see the trees and how they fit into a broader Earth system, the clouds that surround them, the ice that's far north or far south of them, the oceans that really are affecting the climate that is causing those trees to grow.
You know, satellites are really the best way to measure the effects of climate change, because just one person on the ground in one place, it's very difficult to say if what you see in front of you is due to climate change or due to some local phenomena or is just the weather. And from space, we can look at the whole Earth and we can integrate these observations of the whole Earth and really make a better assessment about what's causing these changes and what their long-term prognosis is.
A decade ago, the Earth observing system was beginning to be put in place. A series of satellites designed to observe the Earth, take a snapshot of the Earth over a period of years to understand its behavior. Well, to date, there are 14 Earth observing satellites orbiting right now. And of those 14, 13 are past their design life. They're living on borrowed time and could go away at any moment.
I think funding for these satellite missions is very much threatened right now. There doesn't seem to be a lot of support in political circles right now for these missions, and so that's something that as scientists we're trying to do, is to educate people about why these are so important. Like I said, the GRACE mission has been really, in my opinion, one of the best tools we have for measuring the impacts of climate change on the Earth. It tells us where the water is going. And that's, you know, when we talk about climate change, everybody thinks about the temperature, but it's really the water availability that's going to be the big impactor. And so we'll be able to tell with GRACE, you know, where we're losing water, where there's going to be prolonged droughts, where there's going to be more flooding, where the ice is melting. It's just this wonderful tool. And now we're going to lose this tool for probably 2 to 3 years. And, you know, it's really unfortunate that we've kind of taken away one of our eyes in the sky.
The Earth is changing in ways that will affect our lives. And just as we're realizing how and why these changes are occurring, our ability to understand them is diminishing. And frankly, our future, our success in the future as a society really depends, is intimately linked to our ability to anticipate what's coming.
If you wanted to know the temperature of the ocean, how would you take it? Would you be able to do it in only one spot, or could you find a way to do it across the entire ocean? What if you wanted to see how an area was changing over time? Could you track how the shape of the coastline changes due to erosion, rising sea level, or a strong storm? Or have you wondered where animals like whales and sea turtles spend their time in an ocean? Do they move from area to area based on the season or changing ocean conditions? NOAA, the National Oceanic and Atmospheric Administration, works to answer these questions and more. One way is by using a technique called remote sensing. Remote sensing is the science of obtaining information about an object or an area from a distance. Typically, NOAA uses sensors on board a satellite or aircraft to collect this information. These sensors can be passive or active. Passive sensors collect information about energy that is reflected or emitted from the Earth, like reflected sunlight. NOAA scientists keep tabs on the sea surface temperature around the globe with a sensor on a satellite that measures infrared radiation emitted from the ocean surface. Active sensors produce their own energy. An example is a light detection and ranging, or LiDAR, system, which produces a beam of light and measures the time it takes to go to an object and back to determine the distance. NOAA pilots fly aircraft with LiDAR systems on board to map our coastlines and chart depths of the nearshore waters. These missions track changes of the coastline over time, as well as provide vital data to reopen ports after hurricanes or tropical storms strike. Satellites can also be used to collect and relay information from sensors in remote locations, like a telemetry tag on a whale or sea turtle. In addition to tracking the animal's movements, these tags can collect data about the animal's behavior and environment, helping us develop programs for their conservation and protection. NOAA is an agency that enriches life through science. Remote sensing helps our scientists extend their reach from the surface of the sun to the depths of the ocean floor, as we work to keep the public informed of the changing environment around us.
Can you think of a new way we might be able to collect data through remote sensing? Let us know down in the comments section. And if you like this video, be sure to follow STEM in 30 on Facebook and Twitter, and subscribe to the National Air and Space Museum's YouTube channel.
Okay, so let us continue our discussion on GPS. No? So here are the purpose of the or examples of GPS. But before that, GPS, or Global Positioning System, is a satellite-based navigation system. No? It enables accurate determination of location and time anywhere on Earth. It utilizes a network of satellites to provide precise geographic coordinates to GPS receivers. Again, here are the examples: navigation devices and outdoor activities. GPS is commonly used in a car navigation system, and of course, mobile devices to provide accurate location information. Outdoor activities: GPS is utilized in hiking and other activities for precise location tracking. Again, GPS is a satellite-based navigation system that enables accurate determination of location and time on anywhere on Earth. It utilizes network of satellites. We have many satellites around the globe, that provide precise graphic coordinates to GPS receivers. Itong mga GPS receivers na to? Tayong lahat na gumagamit ng mobile phones. Before, ang gumagamit na ng GPS is the military. Then, napunta sa mga cars. And then ngayon, sa ating mga cellphones, nandiyan na ang GPS. No? So again, to further understand what GPS is, let us watch these two videos. Okay?
Hi, I'm Emerald Robinson, and in this What Is video, we're going to answer the question, what is GPS? GPS is an acronym for Global Positioning System. Many people use the term GPS when referring to the receiver that's found in their car, but that's not entirely true. GPS is more accurately defined as a navigational system that relies on satellite signals to show an object's location. Although scientists have been working on satellite-based navigation systems since the 1950s, the current GPS system's predecessor was created in 1973. It was originally commissioned by the United States Department of Defense for use by the military. But during the 1980s, the government started permitting civilians to use the system. Devices that use GPS work by receiving signals from special satellites that orbit the Earth twice a day at an altitude of about 13,000 miles. A minimum number of 24 satellites are required for the GPS to function, but there are usually about 30 satellites circling the globe in case one fails. GPS satellites continually emit signals that state two pieces of information. 1, the current time, and 2, where exactly above the Earth the satellite is at that time. GPS receivers use this information to do a special calculation called triangulation. The receivers compare the time that the signal was sent from the satellite with the time that the signal was received. The difference in time indicates the distance between the receiver and the satellite. A GPS receiver needs to get signals from 3 satellites to calculate latitude and longitude. If it gets a signal from 4 satellites, it can also calculate altitude. GPS is used in many ways. Scientists use GPS to gather data about earthquakes. Surveyors use it to determine property lines, and businesses use it to track delivery vehicles. A valuable tool since its invention, GPS is changing the way we view the world.
For thousands of how-to and advice.
At over 20,000 kilometers above sea level is a constellation of satellites, each orbiting Earth every 11 hours and 58 minutes. These satellites are continuously beaming data down to us on Earth, which is in turn received by devices such as your phone or navigational units in your cars, allowing you to see where you are on the planet. There are a lot of misconceptions about how GPSs actually work, an example being that your phone and the GPS satellites are both talking to each other. So let's get down to it. How do GPSs work? GPS stands for Global Positioning System, which works through trilateration, not triangulation or multilateration, which is commonly misconceived. There are many different types of navigational satellite systems from countries across the world, but the most popular and commonly used system is Navstar, which is the USA system. There are, however, Russian, Indian, Chinese, and European equivalent systems, although the Indian and Chinese systems sit in a geosynchronous orbit above their countries, which means they are not worldwide systems. The Navstar system, which is simply referred to as GPS, is what we will be focusing more on, although most phones and devices tend to have the capabilities to use both GPS and GLONASS. GPS satellites are set up in such a way that from almost anywhere on the surface of Earth you should have a direct line of sight of at least 4 GPS satellites. This is quite important on the basis that GPS point positioning requires at least 4 satellites to calculate 3 position coordinates and the clock deviation. As GPS units are receivers, there needs to be something sending some sort of signal to devices such as your phone to receive. Each GPS satellite broadcasts a navigational message towards Earth which contains an extremely accurate timestamp, which is obtained through an atomic clock which is on board these satellites. And the satellites also broadcast their position at the time of broadcast, with all GPS signals broadcasting at 1.5752 GHz and 1.2276 GHz. These 2 bits of information allow you to work out your position on Earth. With these satellites all sending exceptionally accurate time down to Earth, your phone or GPS receiver can compare the difference of time between when the signal was sent to when it was received to work out the distance between you and the satellite. By multiplying this time difference with the speed of light, as the signal is sent at the speed of light, you can begin to get the distance away you are from that satellite. As these satellites are also sending whereabouts they are, you can begin to draw spheres around the satellites, with you being somewhere on the outer border of that sphere. As we introduce more GPS satellites into the mix, we begin to get closer to where we are. By calculating the time differences between these satellites, we move from having no idea where we are to being able to pinpoint where we are, to typically down to 5 to 10 meters on average, with the potential error being around 15 meters. There are a lot of factors which escalate the potential error, but the most significant is due to the ionosphere, a part of the upper atmosphere extending from 60 kilometers to 2,000 kilometers, where free electrons occur frequently enough to have an appreciable influence on the proportion of electromagnetic waves passing through this layer. This error is substantially smaller when satellites are directly overhead, compared to being larger the closer the satellites are to the horizon relative to you, as the path between you and the GPS satellites goes through more of the atmosphere compared to being directly overhead. Even things such as small variations in the atomic clocks found on board these satellites can cause major errors. A clock error of 1 nanosecond can translate to a 1 foot or 30 centimeter miscalculation. Then the theory of relativity kicks in, with the atomic clocks ticking ever so slightly slower than clocks which are stationary on the ground, which translates into a 7 microsecond a day delay. General relativity then also kicks in, with the effect of the gravitational frequency shift being far greater than the 7 microsecond per day delay due to the velocity relative to Earth. As the theory states that a clock which is closer to a massive object will be slower than a clock further away, the atomic clocks on board the GPSs are faster by about 45.9 microseconds per day. Combining the 7 microsecond a day delay due to the satellite's velocity relative to Earth and the GPSs being further away from Earth, this adds up to a 38 microsecond delay, which if left uncorrected would translate through to a 10 km a day pseudo-range error, rendering GPSs invalid from the get-go if this was not to be taken into consideration. This is compensated by the GPS's clock's frequencies being slightly slowed down from 10.23 MHz to 10.229999999543 MHz to cancel out the effects of relativity. So next time you turn on your GPS on your phone or other device, you should now realize just how much physics and maths is going in towards you finding your own location. Thank you for watching, be sure to subscribe.
So let us continue the integration of GPS data in GIS for precision mapping. So here are the examples of GPS data in GIS for precision mapping. We have field surveys, asset management, and wildlife tracking. So GPS data is, very crucial in GIS for enhancing the accuracy and precision of spatial information. No? This integration, involves capturing real-time or recorded GPS data and incorporating it into GIS database system. So typically, this is how it works. No? The GPS receivers, tayo, yung surveyors, collect coordinates, latitude, longitude, and of course, elevation data. Then, this data is then integrated or imported into GIS software, aligning the spatial coordinates with corresponding features on the map. So, this is how we collect data and integrate in GIS. Na Una-una, field surveys. GPS data is collected during field surveys, and then can be integrated into GIS for mapping and analysis. Okay. Second one is asset management, tracking the location of mobile assets in real time for efficient management. Next one is wildlife tracking. GPS data from tagged animals can be used in GIS for studying migration patterns and habitats. So sa field surveys, yung ginagawa dito, meron tayong mga surveyors or meron tayong mga tao kung saan they collect data using GPS through field surveys. No? And then, yung makuha nilang data, i-export nila o i-import nila sa GIS. Sa GIS software natin, doon na tayo mag-analyze, magmamapa, no? The next one is asset management. So basically, ginagamit ito sa mga new logistics logistics companies wherein they track the location of their vehicles real time for efficient management. Or for example, yung mga fleet or yung mga taxis, yung mga cars, ginagamit nila itong GPS na to track the location of their assets. Okay? Last is wildlife tracking or naglalagay ng tracker yung mga government agencies sa mga, for example, birds, no? to uh, to uh, to uh, to study their migration patterns. No? 'Di ba nakita nga natin minsan may tinatag silang mga eagles, no? And then after a year or so, kukunin nila yung data na nakuha nila, then makita nila dun yung mapa kung saan pumunta yung mga ibon, di ba? So that's wildlife tracking. So those are the examples again of integration of GPS data in GIS for precision mapping. We have field surveys, asset management, and wildlife tracking. Let us now proceed with LiDAR and aerial photography. So basically, LiDAR or light detection and ranging is a remote sensing technology that uses laser light to measure distances and generate detailed three-dimensional information about the Earth's surface. Okay, for example, we have forest canopy analysis and urban planning. No? So sa urban planning, LiDAR data assist in creating detailed elevation models for urban planning and infrastructure development. So when we say elevation models, ito yung topography or elevation is either kung mataas, mababa, steep, ba? So those are elevation or elevation models. In aerial photography naman, no? Aerial photography involves capturing images of the Earth's surface from an elevated position, no? Usually from aircraft or drones. No? These aerial photography examples is used during land use mapping and environmental monitoring. Okay, in land use mapping, aerial photographs can be used to identify and map different land uses. Again, no? Such as residential, commercial, urban, agricultural, ano pa ba, idle, institutional. Those are the use of aerial photography, sa land use mapping. In environmental monitoring naman, no? Monitoring changes in natural landscapes and ecosystem over time using high-resolution aerial imagery. So kung nakita nyo, no, may mga comparison, may mga images from 1996 to 2020. No? Doon makita nyo yung photography nagbabago from forest area, unti-unti siya nagiging rural hanggang sa maging urban area, di ba? So that's how aerial photography is used in environmental monitoring. Okay, so to further understand LiDAR and aerial photography, let us watch this next video. Okay.
So LiDAR, or light detection and ranging, uses lasers to measure the elevation of things like the ground, forests, and even buildings. It's a lot like sonar, which uses sound waves to map things, or radar, which uses radio waves to map things, but a LiDAR system uses light, sent out from a laser. But aren't lasers used for stuff like, I don't know, scanning barcodes, making your favorite band look awesome, removing hair? Ew. Seriously, how does a LiDAR system use lasers to measure stuff? Now, just for the record, there are different ways to collect LiDAR data. From the ground, from an airplane, or even from space. Airborne LiDAR data are the most commonly available LiDAR data, and airborne LiDAR data will also be freely available through the National Ecological Observatory Network, or NEON, so we'll focus on that in this video. So to get how lasers are used to calculate height in airborne LiDAR, we need to understand the four parts of the system. First, the airplane contains the LiDAR unit itself, which uses a laser to scan the Earth from side to side as the plane flies. By the way, for you remote sensing geeks out there, the laser system uses either green or near-infrared light, because these wavelengths or types of light reflect strongly off of vegetation. The next component of a LiDAR system is a GPS receiver that tracks the altitude and XY location of the airplane. The GPS allows us to figure out where LiDAR reflections are on the ground. The third component of a LiDAR system is what's called an inertial measurement unit, or IMU. Not to be confused with EMU, an IMU. The IMU tracks the tilt of the plane in the sky as it flies, which is important for accurate elevation calculations. Finally, the LiDAR system includes a computer. The computer records all of that important height information that the LiDAR collects as it scans the Earth's surface. No computer, no data. It's as simple as that. Now you may be wondering, how do the laser, the GPS, the IMU, and the computer all work together to get us these fantastically useful LiDAR datasets? Well, the laser in a LiDAR system scans the Earth, actively emitting light energy towards the ground. Now before we go any further, let's get two key LiDAR terms associated with this emitted light energy out of the way. You know, so we can speak LiDAR and all. First, let's define the word pulse. A pulse simply refers to a burst of light energy that is emitted by the LiDAR system. And second, let's define the word return. Return refers to reflected light energy that has been recorded by the LiDAR sensor. So pulses of light energy travel to the ground and return back to the LiDAR sensor. Now we're speaking LiDAR. Now all of this pulse and return business is great, but speaking the language doesn't give us height. To get height, the LiDAR system records the time that it takes for the light energy to travel to the ground and back. The system then uses the speed of light to calculate the distance between the top of that object and the plane. So let's break down what this distance calculation looks like. You take travel time, multiplied by the speed of light, divided by 2 since the light traveled to the ground and back. This calculation gives us how far the light actually traveled to the ground. So using this math, we know the distance between the plane and the ground. But we're not done just yet. How do we figure out the actual elevation of the ground? To figure out ground elevation, we take the plane's altitude, calculated using that GPS receiver. And then we subtract the distance that the light traveled to the ground. And that covers the basics of how a LiDAR system uses lasers to measure height. So now we've got the basics down, but there are two more things that a LiDAR system has to consider when calculating height. First, the plane rocks a bit in the sky as it flies due to turbulence in the air. These movements are recorded by the Inertial Measurement Unit, or IMU. No, not EMU, IMU. So that they can be accounted for when height values are calculated for each LiDAR return. And also, an airborne system scans the Earth from side to side to cover a larger area on the ground when flying. So while some light pulses travel vertically from the plane to the ground, or directly at nadir if we're still talking LiDAR lingo here, most pulses leave the plane at an angle or off nadir. So the system also needs to account for pulse angle when it calculates elevation. So let's put this all together one last time. The LiDAR system emits pulses of light energy towards the ground using a laser. It then records the time it takes for the pulse to travel to the ground and return back to the sensor. It converts this time to distance using the speed of light. The system then uses the plane's altitude, tilt, and the angle of the pulse to calculate elevation. It also uses a GPS receiver to calculate the object's location on the ground. All of this information is recorded on that handy-dandy computer, also mounted on the airplane. And that, my friends, is how a LiDAR system works. Now, there is one more component of a LiDAR system that makes it so useful. A pulse of light doesn't just reflect off of one thing, like the top of a tree, and yield one return. Sometimes a LiDAR pulse travels through things, like the gaps between tree branches and leaves. Think about standing on the forest floor and watching the sunlight filter through the tops of the trees, making the leaves and branches glow. So light energy that passes through the canopy reflects off of the branches and leaves within the canopy. This ability of a LiDAR system to travel through and record information starting from the top of the canopy, through the canopy, and all the way to the ground makes LiDAR systems unique and highly valuable to scientists studying trees. These returns from within the canopy tell us more about what's happening inside the forest, or the forest structure. For example, they can tell us about the shape of the trees, or the density of the leaves on the trees. They can sometimes even be used to estimate whether there's shrubs below the trees on the forest floor. But we'll save that topic of using LiDAR to estimate forest structure for another video. And now, my friends, you know how a LiDAR system generally works. And also, you can consider yourself fluent in the language of LiDAR.